Right, so before I introduce what we're doing today, let me just give you the story so far, all right? We have differentiated a lot of things now that have a y equals something to do with x equation or function. And whenever we do that, we get dy by dx, and that is normally an expression in terms of x. We're differentiating with respect to x, so that is with that is something to do with x. George, have I got your full attention, George?
You do.
Right. Persuade me that I have your full attention by popping your phone away then.
Oh.
Thank you. Just so I know I'm sometimes we meet an x equals something to do with y equation, like in homework, for example. We differentiate that and we get dx by dy. We've differentiated that with respect to y. Y is our variable, but we can then flip that to get dy by dx. But that will be in terms of y, won't it? Because we've differentiated this with respect to y, this will be in terms of y. Sometimes we can do a substitution to turn it back into x, but very often, like the one in the homework, you end up with an expression in terms of y. So here we've got an expression in terms of x, here we've got an expression in terms of y. With parametric differentiation, we have two expressions in terms of some parameter, normally t, sometimes theta. And when we go through the malarkey we went through yesterday, we end up with an expression for dy by dx, but that is in terms of t. And so if you know a point, you have to work out the values of t that relate to that point, and so on and so forth. Certainly with these two types, the relationship between y and x is explicit. It is clear that, in this case, to get the y value, you do something to the x value. Or to get the x value, you do something to the y value. What we're going to meet today are functions like this, where it is not an explicit x equals y equals equation. Instead, we have a function which includes both x and y. So there is a relationship there, but it is an implied relationship. We call these implicit functions, and so what we're talking about today is implicit differentiation. And those of you with the pre-release revision list pinned up next to your mirror or by the toilet will have recognised that from the revision list. So here we go, another thing that we can tick off that list. So implicit differentiation is where the relationship between x and y is there, but it is not as explicit as y equals this and x equals this. It's a bit like Boris Johnson, where if Boris Johnson gets invited to a party that says, please come to my party, then that is explicitly a party. But if he wanders into his garden and sees tables and people having a good time and bottles of wine and snacks, you would think he would imply it was a party. He appears unable to imply that, so he's not very good at this because he's not very good at things that are implied. We need to be explicit. These functions are quite hard to write as explicit functions, and so we leave them like this. And of course, the most obvious example of an implicit function is the equation of a circle. In fact, you might recognise that some of these are very circle-like, although none of them are actually circles. So let's have a look at how we differentiate these things. We're going to do a few of these, and then I'm going to wind you up and get you going, although I've already realised I've left my textbooks in the other room. So we're going to do part A first. We're not going to do all of these. We're going to do 3 of these, and then I'm going to let you go. So first, now I am trying to find dy by dx, which is telling me how y is changing as x changes, which is what we call the gradient. So what it means is x is my variable. So it's easy to differentiate part of this expression. X squared becomes 2x. Always has been, always will be when we differentiate it. 2 is a constant. I know when I differentiate constant terms, they disappear. So that's going to become 0. But how do I differentiate y cubed with respect to x? Well, It's a simple thing which I'm going to justify, but if this next bit completely leaves you cold, it doesn't matter because the way we do it is so simple. I know how to differentiate that. It's that. And then earlier, excuse me, earlier this half term, we learned how to differentiate that. We multiplied by the power, reduced the power by 1, and then multiplied by what you get when you differentiate the bracket. So I'm going to differentiate this in the same way. So I'm going to say, okay, this isn't to do with x, just like this is to do with x, but it's not x, this isn't x, but I'm going to differentiate it using the chain rule. I'm going to say, right, multiply by the power, reduce the power by 1, and now multiply by what I get when I differentiate the bracket. So let me take you back to an explicit function. When I differentiate this, that becomes 6x, that becomes 4. What do I write here? What does y become when we differentiate? dy by dx. So when I differentiate this, multiply by the power, reduce the power by 1, multiply by what you get when you differentiate y, which is dy by dx. So that means, and if that leaves you cold, it doesn't matter because it's really simple. It means when we differentiate implicit functions, x terms, we just differentiate as normal. Constant terms, just like normal, they disappear. Y terms, we differentiate them as if they were x, but we multiply by dy by dx. So it's an application of the chain rule in the same way that with this one we differentiate it as normal and then multiply by what we get with the differential brackets. You don't need to worry about that. In fact, I'm slightly anxious now, that's not in the camera. Oh well. Jacob and Isabel, I hope you can see that. Anyway, never mind if you can't. The rule is simple. X terms differentiate as normal, constant terms differentiate as normal, y terms differentiate them as if they were x, but then multiply by dy by dx. Now, I still haven't got an expression for dy by dx, so I've got to do a bit of algebra now. Taking 2x from both sides. Divided both sides by 3y. And what do I note? Well, I know, remember, when I differentiate an explicit y equals function, I get dy by dx in terms of x. When I differentiate an explicit x equals function, I get dy by dx in terms of y. When I differentiate a parametric function, dy by dx is in terms of t. When I differentiate an implicit function, dy by dx is in terms of x and y. So in order to work out the gradient, I need to know a full coordinate, an x and a y value. So that's step 1, basic implicit differentiation. So let's have a look at C next. Are we happy with anyone to ask about that? Okay, have a go at C next. Okay. So I'm hoping you can do C just using that process as I've described it. When you differentiate an x term, it's just normal. When you differentiate a constant, it will disappear as always. When you differentiate a y term, pretend it's an x, then multiply it by dy by dx. Actually, Joe made a good point in the other lesson. Actually, he said, how can you tell, how do you make it clear that you're now differentiating rather than just doing some algebra? And I hadn't really ever thought of that before, actually. So you might want to sort of say, right, you know, when I'm differentiating, this is what I get. I don't know. I don't think you'd be in trouble. I was using a change of colour to show that I've differentiated.
When you do one is y, is that also going to be
dropping the dot, I'm just going to write it as minus 8 dy by dx. So minus 8x would become minus 8, so it becomes minus 8 dy by dx. 5y squared would become 10y. So I'd write it as 10y dy by dx. Now, because this time I've got 2 dy by dx's in my answer, so I've got to do a little bit of algebra again. And you may remember this is my favourite sort of rearranging, when you're trying to make x the subject and you've got more than one x, you collect all the x's on one side, everything without an x on the other side, and then you factorise. Well, it's the same here. I'm going to have everything with a dy by dx on one side. Everything without a dy by dx, I'm going to shovel that over to the other side. And then I'm going to factorise that left-hand side, pulling out the dy by dx. And then I'm going to divide and because this is a fraction, I can do a bit of simplifying at this point. Remember, we can only do that if every term can be divided or whatever, but every term can be divided by 2. In fact, I'm tempted to divide every term by minus 2, just to get rid of those positives. I mean, you don't have to do this, but what's that? 4 minus 5y. Looks a bit nicer, doesn't it? So that's my dy by dx. Okay, D is the next one, which introduces another step of difficulty.
So it's a D with that.
Yes, D, yeah. So can you see what's going on here? I can differentiate y terms. I just differentiate them as normal and multiply by dy by dx. I can differentiate x terms. Constants, well, 0 just becomes 0, it's already 0. But what I've got here is an x term multiplied by a y term. It's a product. So I use the product rule to differentiate it. So the gap here is going to be what I get when I differentiate 3x squared y using the product rule. And differentiating y becomes 1 dy by dx. So I'm actually just going to write that from now on as just dy by dx. Okay, differentiating y becomes 1, because that's what happens when you differentiate a single term. So the product rule is the one where it's those two multiplied, added to those two. Be familiar with that if you sorted out the homework. I'm just going to run and get the textbooks.
Yeah, if it's a fraction, you take the one twice. I've done boxing to group was like lazy.
So my y term became 3y squared dy by dx. My x term became minus 4. The product became 6xy plus 3x squared times 1 dy by dx, which I'm just writing as 3x squared dy by dx. And do you know what? I wonder if we can do the next bit in one go. Okay. So if I wanted to get everything with a dy by dx on one side, then I know the things I need to move are the 4 and the 6xy. And then that would just leave me with the two terms here, which have got a dy by dx, and I then factorise and divide by those two terms. So I don't want to push you to do that, but it might be that you can do that in one go. So that's just several steps shortened down, isn't it? So I added the 4 and took away 6y squared. That could be written either way, minus 6xy plus 4. That then left me with this and this, which I would have then factorised to give me dy by dx, open brackets, 3y squared plus 3x squared. Again, those can be either way round, can't they? Which I then would have divided by. Okay. (3f), we could use the quotient rule. But believe me, I tried, and it's horrible. We have an alternative. Because we're dealing with an explicit function that we don't need to be written as x equals or y equals, I can actually start with 3f by doing this. So I've just multiplied both sides by x squared minus y, and that's now a product. Product rule is much nicer than the quotient rule. And with implicit differentiation, the equal sign, it doesn't matter where it is, I'm going to use the same rules either side. So I'm actually going to do that one, or I'm going to get you to do that one using the product rule, which is so much easier. Have a go then, once you've done 3, have a go at 4 and 6. So 4 is a equation of a tangent, standard equation of tangent, and 6 is a turning point, although it talks about the gradient equals 0. But it's the same. Some cable management.
Oh, you get triple brackets. Makes me feel like. There's two.
So just 3F, I don't need to do the rest. Again, minus y, I'm just going to write as minus dy by dx. It's minus 1 times dy by dx, but that's, I'm going to leave it. I think you'll note in the answers, I think I'm right. Only one way to find out, I suppose. Yeah, if I multiply everything in that fraction, top and bottom, by minus 1, I get and because it's a fraction, and I've multiplied top and bottom by the same thing, it's just like when you take a half and turn it into 2/4. So that's not what they've got. Oh, it is, sorry, I'm looking at the question. That is what they've got. Yeah, that's right. So when I use the product rule, that becomes 2x minus 1 dy by dx. This times this. That times that gives me that. When I multiply that out, I get that. And then I noted that I've got 3x squareds altogether. So I moved those over, I added y, and again I'm doing that sort of several steps in one go. I hope that's not losing you. You okay, Pat?
Yeah.
Yeah.
Yeah, I forgot to do anything to the right side.
Ben, you alright? Is this?
Yeah, sorry, I went about it a weird way and it threw me there.
Right, right. I mean, it is. It tends to look weird. I think weird is a good word to use to describe because there's always x's and y's and dy by x's all over the place. Sorry, I didn't give you the right page, did I? It's 2, 5, 6 and 7. Correct, that is the correct gradient. Not the subplot, it's the correct gradient, so it's up to work. Uh, 3x times 2y, I'm writing as 6xy. Anyone need a calculator? Yes.
Would the minus 3y squared come that?
Say again, sorry?
Would you be able to get rid of 3 minus 3y squared?
No, because the only thing we can do is divide everything, and because we've got 1, 2, 3, 4 terms, we need to be able to divide everything by 3y squared. If it was one term, if that was all multiplied together, then we could, but we've got 4 terms, so actually they've got no common factors. There's nothing that all 4 things can be divided by. But anyway, it doesn't actually matter, does it? Because all I'm going to do is substitute in 2, 1, so actually we don't need to do a great deal of simplifying. Can I strongly recommend that you store the 2 values? So I'm going to store 2 as my x value. I need to also store the y value, so I'm going to do that. So I'm going to do 1 arrow alpha a, so I've got my 2 values stored as x and a. We can use x and y, there is a y down at the bottom somewhere if you want. And then I'm going to just type that in as minus 2 x minus 3a squared over 6xa minus 3a squared, and that will give me, you should get minus 7/9. I haven't got my visualizer, so I can't show you that. But how can I help you, George?
Sir,
Yes.
in the window thing,
Yes.
when you're timesing 3x by 2y,
Yes.
does it, so it becomes 6, not 3x?
Yes. So 6, I just wrote it as 6xy.
Right,
I mean, you could write it as 3x2y. But
okay.
yeah, that's not wrong. It's just 6xy is a bit neater.
Oh, okay.
So please let me know if you're struggling with the leaving and memory again. It makes it so much easier. Then it's just your normal y equals. I have a feeling they multiply everything by 9. Oh no, they leave it like that. There you go. That's how I would have left it as well. Mrs. Huxton. No, very coming. Yeah, oh, I tell you what. Do you know what? Every now and then I think. I don't be intelligent. Minus 7 ninths times 2 is minus 14 ninths. 1 is 9 ninths. Plus now, those of you who are through 6 will realise how turning point questions with implicit differentiation are punch the air questions because they're very easy. Well, provided one thing. Which question you want? What did you get for your dy by dx? Oh right, yeah, that's correct, yeah. Okay, so you go back to your original function. So you should get a quadratic y.
Yeah, and then you type it into your written.
Appreciate your confidence.
I have to say I haven't done it yet, but so you get
That's hard to do, isn't it? I think that is right.
So when x is 3, you get 9 plus 4y squared minus 18 minus 16y. Minus 9 plus 6x? X is 3, isn't it?
Oh, right, yeah. Yeah, I was just wondering.
At which point you could divide by 4 if you didn't have a fancy calculator, because it falls out quite nicely then, doesn't it? Have you got to there? Is that where you got? Is that the bit where you're saying divide by 2, or are you on a different question? So yeah, you've got minus 2 plus 6, which is like saying, well, you've got 16. Yes, you're right, I'm wrong. Yeah. Yeah, we've got the same, haven't we? Can I just, as always, time is getting on. If you haven't reached this point in the turning point question, doesn't actually say turning point, does it? It says points with 0 gradient, turning points, stationary points. We've got dy by dx, so we're now going to ask when is that 0, and this is the punch the air moment, because 0 is your friend. The first thing I can do is multiply both sides by 8y minus 16. Kills the fraction.
So if it's turning point, why just equals 0?
A turning point is when dy by dx equals 0. So we don't know y is 0. We know x is 3. So what we then need to do to work out y is say, right, let's go right back to the original function and make x equal to 3. That gives you a quadratic in y, and solving that gives you your y values, and there are 2. I'll tell you now. You look troubled.
How did you get rid of y?
How did I?
Get rid of the y?
Right, so I'm asked to find the points where I've got a gradient of 0. So I've got, did you get this far?
Yeah.
So I've asked when does it equal 0? 0 is your friend. If I multiply both sides of this equation by 8y minus 16, kills the fraction, and 0 times 8y minus 16 is still 0. So basically,
Why is it 0 times?
all I've done going from here to here is kill the fraction, multiplied by that. So, you know that when you normally we have equations like this, we multiply everything by 3.
Yeah.
All I've done here is multiplied everything by that. So,
And that would equal 0, right?
and 0 times anything is 0, isn't it? Yeah. So basically we're just saying, in order to ask when that is 0, I just need to look at the numerator. When does the numerator equal 0? So, and that's a really easy sort of question. The tricky bit though is you're still going to go back to the original function, substitute those x values in, and work out the y values. And this was an easy example of a turning point question because we only had x in our equation. What do you do if you've got x and y in your numerator? Well, that's Tuesday's lesson. That's Tuesday's lesson. I'm going to start Tuesday with number 10. If you wanted to have a go at number 7, I'm not going to go through it in class, but that will be excellent extra practice. I commend it to you.
So,
Yes.